every now and then I get something wrong in class. So I want to tell you about something I got wrong about frequency domain systems last class, frequency domain system response last week. So we were working along, we were looking at a system, a second order system. Here you'll see that second order system, and that second order system is in standard form. So that means omega n squared over s squared plus 2 zeta times omega n s plus omega n squared. In systems, this is the most common or the characteristic form. And so, let's go ahead and define that in our MATLAB space. I was working in MATLAB and had this example here with those parameters. This is what we get. So what I did was I built a Bodie plot, and a Bodie plot is how strong a map of how strongly something responds. So the top tells you how much the system responds. In this case, we have a damping ratio of 1/2, and it tells you how much the system responds. And then we've been talking about how frequencies in give us frequencies out. And what I did was I said, let's go ahead and excite this thing with a frequency of 1, and we're going to put in a frequency. So we're creating an amplitude 1, frequency of 4 radians per second, and we're just going to go ahead and put that in with no phase angle. That means that we should be here. So here's that we should be here somewhere around here as 1, 2, 3, 4. So we should be right about here. We're seeing about minus 24 decibels, and again, 10 to the 0 is 1, 2, 3, 4, and so we should have minus 165 degrees in terms of phase angle. So we should so what I said in class was we should get out an oscillation that has minus 23 decibels the amplitude and minus 165 the 165 on the phase shift. In other words, I ought to be able to do that. So I went ahead and simulated that. And to simulate it, I used LSIM, which is MATLAB's command for simulating. Then I just went in and plotted it. So this is about what happened in class. Once that simulation comes through, this is about what happened in class. Okay, and then we looked at the magnitudes of those. We looked at the magnitudes of those components, right? And the tricky thing was we came here and we said this magnitude, if that'll appear, was something like 0.2, and we had another magnitude here, 0.04. So we're looking at something like 0.1, 0.13, 0.15 in terms of our total amplitude. So we're looking at attenuation there, but we're not centered on 0. Looking peak to peak did not give me what we were looking for. So what we started to notice was, let me clear just this one. No. Yeah, what we started to notice was that we had a signal here, the red signal, which is the output, that didn't necessarily agree with just our pure sinusoidal idea of what would come out. So I said I'd figure out what happened here, right? The key to understanding what happened here, and some of you may have guesses, is to look longer at what happened, right? So the first thing that we notice is that we have something that is not centered at the beginning and then starts to decay. And what's interesting to note here is that we do have something. So now we're looking at 0.044 minus 0.086. So we're looking at that 0.13. We're looking at something that has an amplitude that let's go ahead and calculate, but minus 24 dB should be a whole lot smaller than the 1 amplitude that goes in. So let's figure out what our predicted output is, right? So we're going to go ahead and add to this picture our predicted output. Now, if we think it's 24 decibels, I'm going to put that in magnitude units, big M units, and that's going to be 10 to the minus 24 over 20. That's just converting from decibels, 24 decibels to normal ratio. And then we had about 165, 167 phase angle loss. I'm going to put that in radians because MATLAB works in radians. So that'll be my good habit. So I say that what comes out should be this B, this amplitude, a sinusoid at this amplitude that is shifted by a phase angle phi. So let's go ahead and see what that looks like relative to that. So when we do that, we get this yellow line, and we see that indeed after a few oscillations, we do actually arrive at something that really matches that quite well. So our prediction does actually work, but only after about 5 seconds. So what happened before we were at 5 seconds? Let's look at the difference between that. So we're gonna subtract off. What happened there, and the purple line shows us the difference between what we expected and what happened. So this gives us an idea, because what does that purple line look like? It's got kind of this hump where it goes up and then comes back down to 0. So eventually the difference goes to 0, but it has this difference here. We've got a second order system. We're looking at something that more or less overshoots the 0 that we're expecting and comes back to it. How could it overshoot? So this tells us that we have something what looks like a transient response, what looks like an initial condition response, but that doesn't necessarily make sense because our initial condition was 0, right? We put in 0. In fact, I can see that my input starts at 0. Well, so the thing here is that we have a second order system. And so there's actually two initial conditions. What are the two initial conditions? We have position in this case, and we have velocity. So in other words, this system is sensitive to the initial velocity as well as the initial condition. So we have set an initial velocity or an initial condition of 0 in terms of the value u. But the u dot, the derivative of that, is the velocity. And this system, being a second order system, is also sensitive to the first derivative. So if I try to figure out what the first derivative of the input signal is, I'm going to call that u dot. So u dot is a times omega times cosine of omega t. So what I did there was I said in a derivative of sine is cosine, and then we have the derivative of the input of the thing in the argument, which is omega, and that comes back out around. That's our differentiation. So this is the initial velocity, is a omega cos there, and what we find is that is when I plug that in, this is u dot. When I look at u dot at time 0, that's 4, right? I have 1 times 4 times cosine of 0, which is 1. So I have 4. So now I can look at the initial condition. I can look at the initial condition here. So I'm going to go ahead and look at the two different initial condition responses. I'm going to look at the initial condition response. I converted this to state space so I can see the internal states. But I have basically two different initial condition responses. One is the initial condition when I have a position of, let's say, 4 and a velocity of 0. And I get something that decays back to 0. And the other is when I have a position of 0 but a velocity initial condition. In that case, I see something that shoots up and then comes back down and sort of bounces and comes back to 0 again. So this initial, and note that it's starting to die out around 5-6 seconds, right? So this kind of agrees with this velocity initial condition tells me I might be on the right track, right? I may have some transient. So let me see if I can go ahead and use that to reconstruct what we have. So we say what we're going to do is we're going to reconstruct, and we're going to say if I take that velocity initial condition, which is y2 here, and I add it to my YSS, or my scaled and shifted function here, then I ought to get something pretty close. So that's what I put in there. I called it reconstructed. It's the dotted line, and that matches my red line pretty well. So what I'm seeing in this is both the result of the input-output behavior that we expected, the sinusoid that is scaled and shifted, and we're also seeing an initial condition response, which we didn't include in our input-output map because it is an initial condition. So it surprised us here. You will often not see these because often you're forcing your system at different speeds relative to its natural frequency. So you're going to look at how big is omega, the forcing frequency, relative to the natural frequency, and that's going to give you an idea of that. But we did figure out what was happening. We were seeing both the input-output behavior and also the initial condition response because we had a second-order system that was looking at the velocity initial condition and gave us that transient.